We're going to have to do some integration of things like tan squared x, which is their example. Use their examples. Finding some of the others can be harder separate in other books. So I'm using their example, and they want us to integrate tan squared of x with respect to x. Now, for us to be able to do it, we need to have something we can integrate, which is based upon, which is equivalent to the tan squared x, but is one of the differentials we know. So what we need to go through is think about our identities and the sorts of things we're going to get out of this. Our standard identities for double angle formula, so we get seeing things like sine 2a is always 2 sine a cos a. Now that one we can do, if we get a situation where we got this, we can probably do that one by using integration by substitution. We can even use integration by substitution with that one. So I'll show you two methods with this, but they do show different answers. The result of them is two different answers because of the way that the things get combined. Cos 2a, and there's a number of these that we get, so it depends which ones are useful. So we get cos 2a can be cos squared a minus sine squared a. Reasonably easy to deal with, but doesn't help us with our squaring problem. And these are squared. Or we can change it into by rearranging the standard sine squared plus cos squared is 1, and by doing that rearrangement we can get 1 minus 2 sine squared a, and if we rearrange the for cos sine squared becomes 1 minus cos, 1 minus, which can also be 2 cos squared a minus 1. Got those identities. Divide a common one because of this sec squared, that's part of the reason I put it here. We can actually divide through by sine squared. Sorry, cos squared, and we get tan squared a plus 1 is sec squared a. If I divide through by cos squared, I get cot squared a plus 1 equals cosec squared a. And because of that, we can actually get these to work as well. We can integrate now because we now know how to, that these are differential forms of others. So let's go back to the tan squared. Tan squared a, we're going to start off with substitution for tan squared, and tan squared is sec squared minus 1. So it's not a direct translation, but we're going to use that one and change that tan squared a is sec squared a minus 1. That becomes our integral now. So we've got sec squared x minus 1 all integrated. Separate the two parts out, so we're going to integrate sec squared x. Integral of sec squared x is tan x. Sec squared x goes to tan x minus the integral of x of 1, which is just x, and we need some form of constant on it. Let's go for the second version. They want to do one with numbers in it. We've got two others as well still, so yeah. So we want to do an integral with numbers pi over 12 and pi over 8 these numbers, when we get to the point where we're putting the numbers in, we might need to use some special trig functions or trig values. So we want to do sine squared x with respect to x. So we've got to integrate sine squared. How do we integrate sine squared? Well, we've got sine squared is cos 2a down here, so we can use this one. So we're using the cos 2a version, where 1 minus 2 sine squared a. We rearrange it, and we get sine squared a is 1/2 of 1 minus cos 2a. Okay, so there's lots of practice. You do need to know these trig identities and be able to find them really quickly. I quite often will wind up just jotting those down. So it took me maybe 2-3 minutes, but I can now use it in each part. So even when we've got trig stuff going on, we can use that. So I've got sec squared, and we're now going to do an integral for pi over 12 to pi over 8 of 1/2, which the half can come out, of 1 minus cos 2a. If you're using a calculator, be careful. Well, it should be x. Be careful that you are in radians. As soon as you see that we're doing this stuff, we are using radians. Okay. So make sure that anything you're doing on your calculator uses it. This one often, I will say, show the exact value. So you've got to get to there. So we do the integral first, and we've got the 1/2 times integral of that. 1 gives me an x minus integral of 2 cos x. Now you can do it by the pattern, which is a half. And when you integrate minus cos x, it becomes a plus. Sine cos minus sine to cos, differentiating goes that way. Minus cos goes to minus sine, so it's still a minus. The sine of 2x. Well, I've multiplied by the half in both places as well. Sine 2x. Okay, so I partly brought in the numbers and then didn't. We need pi over 8, pi over 12. When you come to looking in here, we now know that we're going to get some numbers I should recognise. So I've got pi over 16 minus 1/4 the sine of pi over 4, and subtract from that. Subtract from that the pi over 12, which is going to be pi over 24, minus 1/4 sine of pi over 6. So now bring the like terms together and use our nice little triangles to work out what's happening. So what we need is, what's the lowest common multiple of these? Well, it's 48, so we've got 3 pi over 48 minus 2 pi over 48. And we got our minus 1/4 of the sine of pi over 4, and if you remember, pi over 4 is a 45-degree angle. Sine would be an opposite over the hypotenuse, or the square root of 2 over 2. Both sets of numbers are useful at different times. So sine of pi over 4 is opposite over adjacent, so I want the root 2 over 2 form. and then we've got pi over 6. Pi over 6 is going to be the 30 degrees, and that is 1, 2, and square root of 3. So we want to subtract the negative, which is plus, and so sine of pi over 6 is opposite over adjacent, 1/2. So we've now got pi over 48 minus the square root of 2 gives this, and that should have a 4 in front of it as well from there, sorry. So we've now got pi over 2 minus 1 all over 8 for our solution. And they've just reversed it in their answer. Let's go for 2 others to try and use our angles. Notice they give us some clue, which can happen in an exam, but I wouldn't rely on it being there. So we want to integrate the sine of 3x cos x cos 3x. And this is one where I'm going to do a couple of methods with it. We'll start off with using the trig identity, and that trig identity is the sine a cos a1, and that gives us a half of sine. So this is going to be 1/2 of sine of 2 lots of the 3x. Now I'm doing my integration. Integrating sine becomes a negative cos. The 6x stays. The 6 also comes out as a denominator, so it's 12, and we get dx. And that is, you can do that by substitution, that piece. There is another answer as well, or another way to do it, where if I actually say u is either sine of 3x or cos of 3x, if I do du dx, we get 1/3 the cos of 3x. And when I rearrange this to say that dx is 3 lots of du over the cos 3x. Now there's a beautiful thing happens here when I rewrite this in terms of u. The sine 3x becomes my u. Cos 3x, oh dear problem, but I also get 3 lots of du over cos 3x. And because this cancels, we actually do get a nice integration we can do. So this is going to become 3u squared over 2, which is 3/2 of sine squared 3x plus a constant. I missed the constant there again. They look like completely different answers. I'll pull up GeoGebra and we'll check the graphs. So let's put in their first one, which is minus 1 over 12 times cos of 6x, and it's working in radians. And if we put in the other solution, 3 over 2 of sine 3x again. Doesn't look right yet, but when we do power 2 on it, sine. Who spotted the mistake? I did the pattern for integration here. I should be multiplying by 3 throughout. So let's just take those out. And So this becomes 3 cos x, differentiating k comes out. Cos x over 3, which gives me 6 here, 1/6 there. I'll put my graph in and change my fraction to what it should be. One over 6. You see the two graphs are actually the same size, they're in phase, and the only difference is the constant is different on the end of the integration. I messed up that dx there, that's a different constant. These two constants are different, but the curves are exactly the same. Now, if you're asked to do anything extra to these, they're more likely to have said, show that this can be written in this form. Okay, so that's by using two methods. There's by substituting an equation, and you can get something which is equivalent by substituting for a function. And as long as that function completely cancels, so there's no x's left, this is perfectly valid.